Okay, now we're talking about electric forces. Electric forces, remember, it takes two things to feel a force. And like charges repel and unlike charges attract, just like magnetic poles. Now, to quickly review, electric fields can exist because of only a single charge. Again, there doesn't have to be anything in the field other than the charge that creates it. Now, electric forces, on the other hand, have to come from two objects. It can come from a charge, or it can come from a charge and an electric field. It's really the same thing as gravity, and that makes a lot of sense in the fact that you can have a gravitational force anytime you have two masses. You can also have a gravitational force anytime you have a mass and a gravitational field. So our two equations. The field force equation, F is equal to E times Q. Again, similar to M times A, force is always force. The second one is Coulomb's law. F is equal to K Q1 Q2 over R squared. Now, with Coulomb's law, we need to understand that it's an inverse square law. And the fact that it's an inverse square law makes it important, as we'll find out later. And K is a constant. It's 9 times 10 to the 9th newtons times meter squared divided by Coulomb squared. It is really just there to cancel out. If you look at your equation up here on the top, you're going to end up with coulombs times coulombs, which is going to be Coulomb squared. So to cancel them out, you have Coulomb squared on the bottom. On the bottom, you're going to have meters squared, so you have meters squared on the top to cancel out, leaving with your force of just newtons. With Coulomb's law, you're going to have two types of problems. You're going to have computational problems and also changing variable problems. So let's start with two 1 Coulomb charges. And between those 1 Coulomb charge, there's a force of F. And I'm just going to tell you that up front. You're going to be told that. Now, in case number 2, what I'm going to do is double R. 2 times R. Well, if you double R, again, it's going to go down since they're farther apart. That makes sense. And it's 1 over 2 squared, so you get 1/4 of F. Now, in the next case, I'm tripling R. If I triple R, well, then I'm going to have 1 over 3 squared, which is 1/9 F. Now, the one that gets people a lot is case number 4. In case number 4, I'm going to have 1/2 of R. I've moved them closer together. Since I've moved them closer together, the force is going to go up, and that makes sense, but it goes up by 1 over 2 squared, which is equal to 4. So you're going to have 4 times the force. Also realize that it does depend upon the size of the charges. If I increase one of those charges, like in case 5, to a 3 Coulomb charge, now what I'm going to have is 3 times the force. So that's the one that goes with that case there. Okay, let's do a math problem. Let's go 1 Coulomb, 2 coulombs, and let's put them 2 meters apart. Now, 1 Coulomb is a really, really big unit of charge, so we're talking about something that's pretty large. So F is equal to K Q1 Q2 over R squared. Now let's plug and chug. 9 times 10 to the 9th newtons times meter squared divided by Coulomb squared times 1 Coulomb times 2 coulombs divided by 2 meters squared. Now, notice how your units, coulombs, and coulombs cancel out. Meter squared cancels out with meter squared. So I essentially have 9 times 10 to the 9th. That looks like 9 times 10 to, let's add a little 9 there. 9 times 10 to the 9th times 2 divided by 4 is equal to 4.5 times 10 to the 9th. And your units are newtons. Now that's a very big force because these are both very big charges. Traditionally, charges are going to be in the microcoulomb range. You'll get something like 1 microcoulomb, which is equal to 1 times 10 to the -6 coulombs. That's a more realistic charge. But for the sake of making the math easier, oftentimes they'll give you 1 coulomb or 2 coulombs or something like that. Okay, let's look at a more complicated one. Now let's look at a problem like this. What we have is 1 coulomb charges at the vertices of an equilateral triangle. And what I want to do is find out the charge on this particular 1 coulomb charge. So let's look at it. Let's think about it first from a vector point of view. We know that forces are vectors, so therefore direction is important. If I just looked at these bottom 2 right here, if I looked at these bottom 2 right here, what would happen is that one would be pushed in that direction. So we'll call that F1. Let's go ahead and call this A, this B, and this C. So that's going to be F due to A. Let's just make it that way. If I just look now at these 2, what I'm now going to do is I have this, and this is F, B. So I get the force of the F from A and the force from B. And now what I'm going to do is put them together. Now when we're adding vectors, remember we always draw vectors tip to tail. So what I'm going to do is redraw B out here. That's going to be FB. The sum of the forces is right there. Okay, so now let's put some numbers in it on the next slide and figure out a way to solve this. Multiple point charges is something that you're going to have to deal with. Okay, now let's solve for FA. FA is going to equal K Q1 Q2 over R squared. Well, K is 9 times 10 to the 9th. Newtons times meters squared divided by coulomb squared times 1 coulomb times 1 coulomb divided by 1 squared. Now I purposely picked numbers to make it a little bit easier as you're first learning. So that is clearly going to be 9 times 10 to the 9th. Again, those are large units, but again, it helps me. Excuse me, that should just be newtons per meter. Let's get rid of that. We just want that. We just want newtons on our answer. Okay, so that's your answer. So let's just slide it up out of the way. Now, what we know now is FA is that. Well, we also know, since the numbers are the same, we also know that FB is going to be that. So FB is also equal 9 times 10 to the 9th newtons. And what we have now is a triangle. We want to find the sides of it, excuse me. So we're going to go, and we're trying to find this side. So we're simply going to say FA squared plus FB squared is equal to C squared. And C is the sum of the forces. So then simply it's going to be 9 times 10 to the 9th. Well, 9 times 10 to the 9th is 81 e to the 18th plus 81 e to the 18th. That's going to equal C squared. When you add these together, you get 162 e to the 18th. So it's the square root of that is equal to C, and that's going to be newtons. Square root of 162 is 40, about. So 40 times 10 to the 9th, if I did my math right. But you get calculators, you can check it. Okay, now if we take a look at that equation, force is equal to E times Q. Again, that's our basic force from an electric field equation. And again, force is force, so it's the one thing that twists its way through every topic we talk about. Well, if we solve that for E, we get E is equal to F over Q. Okay, let's put in Coulomb's law now. K, Q1, Q2 over R squared divided by Q. One of your Q's cancel out. Doesn't matter which one you cancel out. And you get that E is equal to K Q1 divided by R squared. And that was our electric field equation that we had earlier. So it's important to understand that those go hand in hand. Remember, the force is always with you. Hope this helped.